Stefan Engblom, coming to us from Uppsala. He's going to tell us about stability and strong convergence for multiscale methods for spatial stochastic.
Thank you, Ruth, for introducing. Yes, and thanks for hanging in there after lunch. So I'm going to talk about some work I've been doing the last couple of years involving theoretical investigations into what is meant by this type of mesoscopic stochastic models that I have taken an interest to. So the left application will be a firing of a single neuron, so that's the most biological part perhaps, but it turns out that actually the same type of computational models are quite useful also in the epidemics situation to the right. So this is on a national scale epidemics. So I will give you both actually, from the very small scale to a quite big scale. So the outline is, I will give you a very short introduction to this computational framework, stochastic reaction transport modeling in compartments, and then I will remind ourselves why this type of modeling is interesting and what demands these reasons put on the modeling itself. And then I'm going to work through a bit of the analysis that I have been able to work out together with some collaborators. And as an example of this, I am going to show you how to understand convergence of a fairly elaborate multiscale variable splitting method. So this is the type of methods which are useful when trying to bring out parallelism or to improve the efficiency of stochastic simulations by doing certain deterministic approximations. And then I will show you these two applications as examples of the theory. So the idea with this reaction transport framework is then to put together something like a local physics and some kind of transport mechanism. So in this figure to the left here you have this primal triangulation in black, and you have this dual mesh which is in blue, and the state of this system is then to count the number of agents or molecules or species within each of these dual voxel. And then within such a voxel you have some kind of local physics, and the typical example will be reaction physics, but you can also think of other types of physics which works well in a kind of local environment. And then you're going to have transport events or molecules or agents or species will move between these voxels according to some other connecting physics, a transport physics. So then the idea is that, for instance, if you're looking at a computation in a cell, you could do a triangulation or make small voxels, and you can have quite different physics within this cell and then connect it with a transport mechanism of some kind. So in a sense, this is a bit like a PD framework, and maybe the main difference here is that I consider space to be discrete already from the beginning. So it's not a space continuous model, space discrete and continuous in time. So how to build this up? Start with this local physics. So the example here would be some kind of microscopic understanding of a bimolecular reaction, X plus Y goes to Z, but it could also be this kind of infection spread dynamics, which looks quite similar, or something else that you have taken an interest in. And then we go to the mid image there, and basically this is what the situation could look from as a little of a distance. You have some kind of Brownian motion, say, or some transport mechanism before these blue and black molecules are close enough such that you can apply this local physics. And then you're in this situation over here that you look inside one of these voxels, and there the local physics is basically this reaction mechanism, and you can assume well stirredness or some other conditions if you like. And when you're counting individuals like this, then it so happens that a continuous time Markov chain is the most immediate model of this physics in this locally zoomed in situation. So it comes quite naturally. So then we take the transport physics next. So the typical example would be Brownian motion, for instance. You have one heavy particle surrounded by many smaller ones in a fluid, so you get something which looks like the middle image there, a Brownian motion, Wiener process. And then if you do this voxelization, you make a computational mesh, you will have something that jumps around those voxels, basically. And so then the idea is to build a kind of mesoscopic transport model which works on this mesh directly. So you don't know exactly where the molecule is, You just know what voxel it currently occupies, so it jumps around according to this transport physics, another Markov chain. So the purpose of going from the microscopic to the stochastic model in the middle there is that the stochastic model is simpler, but it's random. So there is an error in the form that the microscale effects from the surrounding fluids, they are there only in a statistical sense in this white noise process. When you go from the stochastic model to this mesoscopic compartment-based model, you do an additional discrete space approximation. You have a finite mesh size h basically. So a reminder, why should it be stochastic, discrete, and why space? So I decided to do a total self-citation here and look at old text that I have written. So the first one is from when I was a graduate student, and I liked very much when I read it now that this inherent stochasticity of the system plays a vital role. I kind of think it's quite nice in a nerdy way. And then we have this intrinsic noise impact, a large impact, and you have an extremely complex kind of environment. So actually discrete and stochastic is really, really necessary. And then you have this biological realism compared to PDEs, but it's quite manageable to use it for complexity, for computational uses. So there have been very many similar remarks made by many others, and I'm sure in the audience there are many of you have also written similar remarks. So in a sense, everybody kind of knows that, yeah, okay, stochasticity is important for various things. But let's look a little bit further. So we want to use these type of stochastic mesoscopic models when either one of stochasticity or nonlinearities or species discreteness or spatial inhomogeneities make a big or at least an interesting difference. So the physical model that we sort of want to manage is itself quite sensitive to perturbations in any one of these. So we start from that. It already is quite sensitive. And then if we are dealing with understanding or designing computational models, either we do some kind of analysis by analogy, like we think we understand where the problems are and we try to get away with it and maybe do some experiments and see if it is close enough. But I think that when you want to analyze this hard enough, in the end you're actually using this Lax principle, the Lax principle of numerical analysis, which basically tells you that if the approximating physics approximates wanted or true physics, then the numerical solution converges to the true solution if and only if the numerical physics is stable. So if you have a right-hand side that approximates another right-hand side, basically, this is consistency, then you have to prove that the numerical approximation share the stability properties of the mathematical model that you want to approach. So this is the Lax principle, basically. So a little bit notation. So this is the well-stirred or local physics case. In this case, I have a state X, which just counts the number of each of these species or agents or compartments, kinds of agents. And the events of this model or the reactions, they are transitions between these states. So I go from X to X minus NR. And NR is a vector in the stoichiometric matrix. And there is a propensity WR. And if I write it like this, there is a Poisson representation, which is the one that I'm going to use in this talk. So X of t is equal to the initial state minus the sum over all these possible reactions or events that can happen times how many times they have happened since time 0, basically. And each of these pi r here is just a unit rate Poisson process. So this is sort of the SDE, if you want, that I'm going to do approximations in. So if we go to the spatial case, so now we have taken this volume, this cell or this country or whatever it is, and we have subdivided it into small enough computational cells such that this local physics that I talked about in the beginning is now considered to be an accurate model, the well-stirred kinetics, if you wish to call it that. So now the state of the system is instead an array. So I have d by k elements, and d is the species again, and k is the number of computational cells. So I have these local physics events from the previous slide, and they happen vertically in X in the same column because they sit at the same voxel. And then I have transport events which takes you horizontally in X and basically transports you from one voxel to another. So the model of this looks as follows. Reactions, I already said it was the same in all of these K cells. So just duplicate the local physics throughout this computational volume. And transport mechanism, in this talk I'm going to talk about a linear model. So the number of species to the left here, xij, transport to some other cell, x in k, and that would be xik. And the rate at which this happens is qijk times the number. So it's a linear law, basically. And that's enough for convection and diffusion, but you can also show that you can approach certain crowding approximations if you want. So this is basically for convenience in the talk. So if you write down the law for this in Poisson representation, it looks like the bottom equation there. So you have outgoing to begin with. Those are the agents that leave the current cell. And then you have incoming with the plus sign. So that's cells coming from another cell going inside the present cell, J. So what is usually called the reaction diffusion master equation, I call it just the reaction transport framework here, is then combining these reaction, which is the first line, with these transport events. So now we have local physics and we have a transport physics. So it's like a thing which has been formulated in already discrete space. So I assume there is already a mesh here, basically. And the limit when this cell size goes to 0 is not so straightforward. There are ideas of how to do it, of course, but it's not just to take the cells to 0 in this representation. So I'm going to start with the well-starred case because it's slightly easier. So in that well-starred case, without space, we have something which looks like an ODE. So to get some ODE feeling, this continuous time Markov chain could be thought of as something like x prime is equal to minus the stoichiometric matrix times these rates, W of x. So that is something that, what is the feeling of this? I put a norm on this, and this is just a simple counting norm. So I have a weight vector L here, and I multiply the species of this by this weight L and sum them together. And this becomes a norm because it's a positive entity here. So I'm adding positive things. So it's x cannot be negative, for instance. And here are my assumptions. I'm going to refer to these three somewhat loosely as the blue assumptions. I'm going to try to use assumptions in blue so you know what assumptions I'm talking about. So the first one basically tells you that if you look in the direction of this vector L, then the dynamics is at most linear in the L norm. So you have A plus alpha and then the norm of the L norm of x. So it can be at most linear in this direction. And then you have to have a certain absolute bound as well, where you have a square over there. And I can allow these to be quadratic. But there are some complications of the theory when you have beta 2 here non-zero. And there is also a local Lipschitz assumption, which is not super important right now. And I should just say also that number 2 here, that's the added thing that you need for the stochastic case. The ODE case, you could get away with only the first one, so you need something stronger. Then a summary of results. What you have then is that if you have suitable initial data to this local physics or this well-starred kinetics, then you can prove that this rather strong bound of the norm of the process is bounded for any p. And you can prove that if you start at the same point, which is quite obvious, then you should have the same one single trajectory. And there's also a condition that allows you to have an ergodic result, so that the moments stay bounded indefinitely with t as time goes to infinite. So this is usually you would want that if this is some physical process, because otherwise it looks as you're modeling incorrectly. And there are two important things. If you start at the same point, almost surely, and if you do a delta perturbation of these intensities in a relative sense, then you have that it's a continuous perturbation in the root mean square sense. So these trajectories go to each other. And this is very important because otherwise it would be very difficult to calibrate the model. If you make otherwise a very small delta perturbation of one of these intensities, just modify the rate a little bit, you could potentially get a totally different trajectory, and it would be very difficult to calibrate. But this guarantees that you kind of could take data and calibrate on top of this. And there's a typical thing also that if both processes are bounded, if you have some a priori absolute bound, then you get an order estimate, and this will actually come later as well. So moving over to the spatial case, and this is just one small thing that we need to be able to handle this case. So then we had this well-starred physics first, and we also had this linear transport law here. And to get some PD feeling for this, it looks like the expression I have written there. Vt is equal to some kind of reaction physics and some kind of transport law. And you can think of this Q here as maybe a numerical approximation to a kind of diffusion operator, for instance. That would make sense. So it's an approximation in this already discrete space, a numerical approximation of some kind. And the one, I have two more assumptions. I need to do some quite weak assumptions on the mesh. I skipped it, but they are not very strong. And on the reactions, I add this assumption of density dependent. So each reaction intensity or each local physics intensity should scale with the local volume in this way. And this new function UR here does not depend on volume anymore. So you have gotten rid of the volume dependency there. And it's actually the same U that goes into the PD here. So they are connected in this way. So those are the assumptions. So the results here, I have a new norm, and a thing to note here is that this is a mesoscopic norm. So I'm counting individuals here. I sum the L norm up in each volume. I do never scale by the volume here, for instance. So this do not go to some kind of integral. It's a kind of counting norm due to the modeling, basically. So if I have only reactions, it's the same local physics in many voxels. So I have, logically, I should have the same result as before. If I have pure transport, then actually I have that this norm is preserved exactly, because it's just the same agents that move around, so I never increase it by anything. So it's just bounded by the initial data. And then if I couple the spatial and this local events together, I get something which is well behaved as before, basically. And I also have this strong continuous dependence on parameters, so I can still do parameter estimation or calibration within this framework. So I'm now going to show you an application of this, a multiscale variable splitting. So this is a case where there's separation of scales. And I think here that species are either abundant, so then they are proportional to epsilon inverse, where epsilon is supposed to be some small number, or they appear in low copy numbers, like 1. And the rate constants, they are either going to be fast, meaning 1, or slow, epsilon. And there are a few more details on that which will come on a later slide. In any case, you can imagine that there's a rescale variable, x bar, which I have scaled such that it's roughly 1. So all of these abundant one I would multiply by epsilon, and the other one I just leave. So that's a new x bar variable. There are two methods or two errors that I can think of here. So exact, I call it. This is here you can observe the multiscale error. So I call this y bar. And basically what I do there is that I take any Poisson process, any stochastic Poisson process there, and I replace it with just the mean drift term. So instead of pi of t, I use just t. So it's a very simple model in this case. So this exact simulation method is going to have a kind of multiscale error compared to x bar, because I have simplified, removed some noise of that. There's next a numerical method, which is the same as this exact one, but much more effective to actually simulate. So here I freeze these abundant species for one time step and integrate the stochastic ones. And then I switch the roles and freeze instead the stochastic ones and integrate the abundant ones. So this is a very practical method. And there are going to be an error from both of these approximations in turn. So the scale separation, here are the details of that. So I have a scale vector, which is just 1 or epsilon inverse, according to which species it was. And then I assume these scaling laws here. So the linear transport just pops up, this epsilon to minus mu, and provided that I do the scaling S inverse for the argument. And for the nonlinear rates, it's a kind of similar thing. So these Q bar and U bar, they are understood to be O of 1. So I have removed the scaling there, basically. So now I have to establish existence. Does there actually exist such a scale-separated solution? Is it meaningful to talk about it? And if you compare to these blue assumptions, these are very similar, but I have to enter the scaling somewhere. So I have to put that in somewhere. And all of these parameters are now have to be independent of this scale parameter epsilon. And if this holds true, then I have that in an O of 1 interval of time, with O of 1 initial data, this rather strong norm is also O of 1. So hence there is a scale, it's meaningful to talk about a scale separation in this case. Otherwise it could be that one of the mesoscopic stochastic species went very big, for instance, and that would violate this idea. And then I need to ensure that these numerical approximations, the exact simulation and this numerical split step approximation, are also O1, and that there's a scale separation for those as well. And basically what I have to do is that I have to go into the assumptions of the previous slides, number 1 and 2 here, and then I have to modify them a little bit for y bar and y bar h, basically. So there's a couple of technical details to think of there. And finally, the multiscale split, I put these low numbers in group 1 and large numbers in group 2. And now I have R of group 1 is the collection of all transitions that affect any one of the species in group 1, and the same for R of G2. And then there are two exponents, U and V, that goes into here. And basically U here is the worst epsilon scaling of a transition that affects G1. And V here is the worst epsilon scaling of a transition affecting G2 plus 1. And the reason there is a plus 1 is that this is the macroscopic species, so I have one scaling for free in a way there. So finally, errors. Under those collected blue assumptions above, you have a certain error estimate. So this is for the exact simulation, where I just replace Poisson processes with integrals, and this true physics, which is just scaled, and there's a certain error estimate of it. And interesting here is that the bounded or the unbounded case is almost the same here. There's a little bit difference when U and V go to 0, but they are very similar, these results. And under the same assumptions, you also have a split step error estimate. And unfortunately, in this case, if you are in the unbounded case, you can only prove convergence. So the error estimates are very difficult to get at in this case. And to conclude the theory, here is a very simple example just showing at work, and this is kind of a stress test, because even though it might not be a super realistic example, it kind of tests all part of the theory. So you have two species that are macroscopic, two species that are mesoscopic, and then you have diffusion of different speeds, and you have some scale separation because of how these reactions are coupled to each other. And you get this very nice epsilon 1/2 convergence, and you have a proportional to h convergence when you look at this in the root mean square sense. So finally, I will look at the applications of these kinds of ideas, or these kinds of solutions. So in the first one, I'm going to solve a multiscale neuron model, where I'm going to connect this ion channel gating process, a continuous time Markov chain, with some OD for the membrane dynamics, which is these classical cable equation style. And I'm going to further couple this to a PD to actually propagate this local field potential in extracellular space. So this goes in many directions, this coupling. So the bottom level is going to be one of these, a sodium channel, a continuous time Markov chain. And basically, if you write out an equation, it looks like a chain like this, where you go from N0, which is closed, and you go through some intermediate steps, and you get to N3, which is open. And all of these rates that are dependent on the voltage. So the voltage which will change the speed by which this process happens. And to effectively be able to do this, we do the split step approach. So we freeze the voltage for a short period of time tau. So I integrate with this kept fixed. So this is like this split step method. At the middle level, there's going to be a cable equation, and it ends up being an ODE like this. So we put in here the number of open gates, N3, and you are going to propagate this ODE, this cable equation, and the output of this is this transmembrane current IM and this voltage along the neuron, basically. And we do this actually using true neurons, which we have downloaded from a database, connect them together. Finally, the top level, this is just Maxwell's equations in potential form. So you connect to the voltage in extracellular space, and you put this transmembrane current here and put it as a source, basically. And when you put it all together, it looks like this. So here we have an ignition at the bottom here, and you give it a current there, and that will drive all of these compartments containing ion channels. And the ion channels will then go to open, switch between closed and open, and you get this current along the neuron, and hence a voltage, and then you propagate the voltage in extracellular space.
I'll find your grid on that.
So this is, there are two grids here. One grid is on the neuron itself, and that's treated like a curve, basically. So it's not super thin, it's, well, let's say a couple of 100 points or something like that, connecting like linear segments. And then there's another grid which is in space, in 3D space around it, which is fairly resolved close to this curve, such that you have one vertex of each neuron point in that one, but then slightly coarser when you go away from the neuron.
What is the color code in terms of the intensity of the rate compared to the color?
So how strong it is, I couldn't take, I think I removed the bar here, actually. But I would have to check it up. There's some numbers there, but I don't know what is exactly the units.
And how many channels are you including?
This was the sodium channels, so 4 per each little compartment, and the number of compartments along the neurons could be, I don't know, 100 or something. Like each of these line segments would naturally have one such state, basically. So that was on the microscopic scale. Now I'm going to national scale instead to finish off. So this is a model of a spread of E. coli bacteria in the Swedish cattle population. This particular strand, O157H7, is a really important zoonotic pathogen. So it comes from animals to humans, and it's of a very great public health interest because you can get quite seriously sick from it. So in Sweden we have roughly 500 cases annually. If you're grown up, you will probably go to hospital, or you will be off work for a couple of days. If you're young, it's typically hospital, and if you're really young, small kids, they can even die from this, so it's quite serious actually. There was one event in 2011 in Germany, for instance, where you have almost 4,000 reported cases and 54 people actually died from it. And the important thing from the modeling perspective is that the infected animals, they show no signs of the disease. So it's not like a zombie disease, and you see zombies and you kind of shut the city down. They are just normal cows. They look and behave healthy. But actually they shed the bacteria to the environment, and it's quite hazardous for people to move around these cows. So this is part of some ongoing research to better understand this epidemiology. And we have data for this, so we have a lot of data. It looks like this. A lot of many events of cattle exiting and entering this database. Is roughly 1.6 million cows for 10 years. We have internal transfer, meaning that they changed age category. We also have an external transfer, which is how they transport around Sweden. So the transport physics here is physical event, like I actually tell it to move an individual from one compartment to the other. And then, so this is what it looks like. This is a week of transports. So you might be somewhat, you have external transport, you have between 4,000 to 15,000 transports per week, which might be surprising that it's so much. And I wrote down here that the population between UK and Sweden is 10 to 1. So I could estimate that you're probably having 10 times this in the UK if you do the quick approximation that the number of cows is proportional to the number of people. So this is what it looks like in Sweden, at least. And here's the model, this local physics. It's a cis-E model, so susceptible to infected to susceptible back again. And this is mediated through this environmental infectious pressure. So you have infected going to susceptible, so they get rid of the infection, and this is just some rate gamma. And then the rate by which you go from susceptible to infected is also a similar rate, but you also enter this environmental infectious pressure, which is basically the number of bacteria in the environment around you. And then there's this OD, so there's a kind of scale splitting here. This infectious pressure is driven by an OD, where all infected cattle shed this to the environment, and you have a certain decay term here, which stands for the removal of bacteria. Epsilon, there is an extra term, which I will shortly discuss. And when we try to calibrate this from actual data, it's known that you have roughly 4% cows infected at any given time. Then we found that this beta here had to be dependent on time, or dependent on season, because the Swedish, if you look at the map, basically, you see that it's quite different in the south and in the north, and up there it's quite cold, so actually this decay is probably quite much faster. The bacteria doesn't like so much to live up there. And another thing that is interesting is if you take this ad hoc term epsilon and put it to 0, then contrary to the corresponding ODE model, there's finite time extinction. So this model always, the disease always dies out in finite time, and it's quite short time actually. So if you look at this model without the epsilon, typically we expect the infection to die out in like 2 or 3 years or something like that, and that is not observed. So it's thought that there's some additional terms that gives you bacteria somehow. But that was part of the deal. We're supposed to be using when there's a big difference to the ODE case. That's sort of where we're building these models. And finally, this is what it looks like if you simulate it over time. So there's a couple of years of data, and we can follow this number of herds and the prevalence, how many percent have this bacteria. And this model is quite good and predictive in all parts of Sweden except for in the middle north. There's an extra little spot there which cannot really be explained by data currently. So we believe that there's some extra calibration to be done here, because it's known that the cows up there are pretty healthy actually. So to sum up, I have talked about this mesoscopic stochastic reaction transport, an event-based computational framework which allows for fairly intuitive modeling and coupling between different types of models. So the terms and conditions were such that, stochasticity, nonlinearity, and so on are important. And if you use this when it's required, then actually being able to have convergence, actually being able to rest on analysis to prove that a certain model is an approximation of something else is puts some constraints on methods development. I also briefly talked in words about this lax principle, which ties together well-postness, stability, consistency, and convergence. Convergence is then what you're after in the end. I did an analysis of simple numerical methods, and quite some effort is required to put down the assumptions on the model. When is the model correct, when it's well-posed and stable, and then you have to find similar assumptions on the numerical model as well. I showed you 2 examples. One was this multiscale split-step neuronal application. It was a kind of a proof of concept for how to couple quite different types of models. I also showed you on the other scale of the spectrum a national scale model which is completely driven by data, and also some interesting findings when attempting to fit these parameters to data. So that was it. Thank you very much for your attention.
I have a question. So as I understand it, the first half you said, okay, it's a well-controlled approximation. If you take your grid small enough, you'll get the right physics.
No. So what I said here, because those are very interesting questions, they have to be basically here. The grid has to be given and fixed. There are some conditions on it, but they are quite
Sure.
they are not very strong. But to start to squeeze the voxel size down is complicated, and you have to take care of the physics then.
So the epsilon and the h were
No, they are. It's a fixed mesh basically. So this is just connecting the transport with the local physics happening on a fixed mesh. So the h has nothing to do with the voxel size. It's the time step.
the time step. So the discretization of the time step is well controlled if you get it small enough. So the question is, when you're applying it at the end, is that a problem? Like, are you ending up conveniently having to have a very large time step, or are you fine?
Yeah, I think it depends a little bit. I mean, the problems you're after by doing that is basically when you have some kind of stiffness. So things go in different ends, and you may have many events really doing nothing in a way. And you can always set such a problem up that it's very difficult or very noisy or very chaotic. But in the good places, when there is a slow dynamics that is the one you're after, hopefully you can rescale it and then put basically a kind of ODE method on that part, so you get some kind of mean drift. But like said, I have the conditions here, and they are somewhat involved, and they guarantee convergence. But you can always find a very strong nonlinear problem where it's just chaotic, and if you try to do it in some way, it's not going to work. Like, there's no clever method for it. So the conditions, they are there, and for the models that satisfy those conditions, there's convergence. Yeah.
It's a more meta-level question, not specifically related to what you say. I try to understand how applied mathematicians work. All the conditions that you say, the mathematical conditions to justify approximations, how much are they sufficient and necessary to do scalable simulation that gives you information of the phenomenon?
So I've been working a little bit of having, if you, let's say, feed in a model, like can it find the assumptions automatically? And it is possible for certain classes, like reaction kinetics, you can pretty well say if it's going to work or not, like you can probably see that. And these are sufficient conditions. They are not tight, so you can probably relax them even a little bit at lots of complications of the theory. However, they are also quite weak. So most models that I have come across, they are basically satisfied quite easily. So they are not very strong, these assumptions. Like the weakest one is probably locally Lipschitz. Like that's very simple. The other ones have to do with growth basically, and usually they are satisfied.
I meant more sufficient and necessary, not inside the mathematics, but
in the computation.
In
You mean if
the
it's
phenomenon that you want to model? If people are doing it for cultural reasons, or
yeah, I don't know. I think, yeah, for these models I showed you, at least it's satisfied and it makes sense there, but there's probably always going to be another class of interesting models that goes out. So there's always more work to be done, I guess.
Hi, Stefan. So if you use second order strang splitting, can you prove anything?
No, that's a good question actually. So the second order, it's second order in the operator sense, of course, whereas what I showed you here is first order in the operator sense. And I have looked very hard on the theory, and you cannot prove anything in the strong sense. So they are both half order strong sense convergent. However, what I have seen from some examples at least is that the second order scheme, which shouldn't be called second order scheme, but it's more accurate. So you have like an order of magnitude more accurate, but you still have linear convergence. So it's an interesting thing, and I have no ways to explain where the constants somehow get smaller. But it's more accurate, but it's still only.
You don't change anything apart from doing the strang splitting?
No, you can fit the second order in the same theoretical framework, and you would have the same theory, and you cannot really see that the constants should be smaller, but apparently they are.
One thing that if you do strang splitting, you're using delta T over 2 for one of the processes.
Yeah.
And that can dramatically reduce errors, like if the faster process you put on the outside of the strang splitting. So you have to compare That could be
it could be that you are comparing apples and oranges somehow. I think the case I tested was just super simple, like linear birth death, and just to see what happened. And in that case, there's no they are both the same speed. But I think that if you have scale separation, you can have either more difference or less difference depending on the setup. So yeah.